Okay, so yes, so indeed the second part is on, well, yeah, it's quantum biology. It's not about all of quantum biology. It's mainly about photosynthetic complexes this time. I certainly changed a bit compared to the one that I gave in Strathclyde. So for those of you who have been at Strathclyde, there will be one or the other new thing in there. So, and for those of you whom it's new, I mean, so it contains all the introductory part as well. So it's fine, I think. So that's the one that you saw yesterday, and actually, could I put it? No. Oh, that's too bad. Okay, so that's the slide that I also had yesterday. Yesterday I used it to motivate that we want to develop sort of new tools, new sensors to study well, biological systems or generally smaller systems. And well, today I used the same slide to motivate why we might be interested in quantum effects in biology. And well, again, so if you start up here, you have classical big objects like us, and so it's clearly a biological system, and it's pretty clearly a classical system. There are a small number of people who think that maybe the brain is a quantum computer, but I regard it as rather unlikely. But then, well, when you work your way down, you get to smaller and smaller structures. And of course, what we know is that if we work our way really far down, then we arrive at individual atoms, because everybody in the world is composed of atoms in the end. And atoms, of course, are quantum mechanical things. You have to really understand atoms, molecules, and chemical binding and so on. You need to understand a bit of quantum physics, and to get a quantitative understanding, at least, you really need quantum mechanics. And because down here the world is quantum physical, up here it's classical, it's evident that there should be a barrier, well, not a barrier, sort of an area in between where you have a transition from the from the classical world into the quantum mechanical world. Okay? And the question is where this barrier or this transition region really is. So, and in biological systems, so I mean, it's clearly here's quantum physics, this is the classical thing for it. So where exactly is this transition region? And not only that, so what we also would like to understand is to what extent, so we know that somewhere deep down quantum mechanics plays a role, to what extent is it actually necessary for us to really use quantum mechanics to describe maybe fundamental biological problems, processes to really understand them? Might it perhaps be possible to just always use sort of a rough classical description to understand the fundamental processes to a sufficient extent that we understand all biology? Or put it more extremely, will at some point biologists have to take a quantum physics course to really make progress in their science? And another question that you may ask, and that might be of interest, is so if there's this transition from quantum to classical, surely this region is a bit it's a bit shaded here. It's not a complete sharp boundary. And in fact, we know that in quantum information processing, for example, we make a great effort to push this boundary in this direction. So we want to make more things quantum mechanical. We want to construct quantum many-body systems where all the interactions between them are quantum mechanical, and where we in the end build a quantum simulator or a quantum computer or something like that. So we certainly try and push this boundary towards this direction. And we do this because for us we have found ways, at least theoretically, we have found ways to make use of quantum physical properties, to make them work for us, and they are of advantage for us. It's not so immediately evident that biological systems would do the same. It's not clear what quantum properties properties might be useful for biological systems, for example. It could also actually work the other way around. Perhaps nature tries to push the boundary downwards. And in fact, if you think about it, sort of 20 years ago or so, people were rather thinking of quantum effects in electronic devices, in some cases at least as a bad thing. So there was always this statement of, well, we have Moore's law and all the structures on our microchips become whatever, half the size every 12 to 15 months or so. And at some point we will hit the situation where capacitor is charged by an individual electron, or the structures become really atomic size, and then quantum fluctuations might play a role and might really be a bad thing for our devices. They would not function, at least not in the way we are normally expecting. So people were thinking, oh, quantum effects might be a bad thing. So maybe that's the situation in biology. Maybe quantum fluctuations are really a bad thing, and nature actually tries to suppress them by putting in a lot of noise, for example. So it's not completely clear what nature does here. Does it push the barrier, the transition region down or upwards? And so these are kind of questions that you would like to find out. And now, the next thing that one has to clarify is what kind of questions would we be asking? Well, on the one hand, you can ask questions like in a quantum simulator. You would often sort of try and simulate the ground state of a quantum many-body system. So you want to prepare it in the ground state of a wonderful quantum magnet, and then you make some measurements, and then you may make some slow changes to see a quantum phase transition. Well, biological systems, I mean, what is really important about them is that they are dynamical processes that are really making life. I mean, I'm not a sort of a static object. I am in a non-equilibrium state. To maintain this non-equilibrium state, my body actually has to do quite a bit of work, taking in food, transporting around stuff in the body at all levels, in the blood. Proteins have to be transported around, charges, electrons, all sorts of things are being transported, and all sorts of dynamical processes are happening that make sure that I actually remain alive. So really what we would like to study is the relevance of quantum physics, or the potential relevance of quantum physics in dynamical processes in biological systems. Okay? So, well, I don't know. So, okay, so what kind of questions would you ask? Well, okay, so in dynamical processes, that's the important part now. So first thing we would like to actually find out, well, is there coherence or quantum coherence? And if there is quantum coherence, on which length and time scales? Well, if you look at a sufficiently short time scale, you will always expect to see some quantum coherence in the system. If you keep the system with a laser, for example, and you look a femtosecond later, you have a good chance that there might be some quantum coherent dynamics, because simply the system hasn't had chance to sort of interact with the rest of the world to decohere again. And so it's always also a question of what time scales, on which time scales you may actually see quantum coherent dynamics. A femtosecond would probably be a touch short for being relevant to biology. What we will see is that picoseconds or so are time scales where you see quantum coherence, and it is relevant to biology. Okay? So there are reasonably fast processes that take place on these time scales. Well, you would also like to see how, I mean, sort of quantum coherences might pervade in space, and over which length scales you might have those. And these are, on the one hand, theoretical questions, but also stuff that you would like to study in an experiment. And well, once you find that there's quantum coherence, then you better find out, okay, is it there just by accident because somehow the world deep down is quantum physical, and so there's some leftovers of coherences? Or is this coherence, or this coherent dynamics, actually really being exploited and made use of to optimize biological system, to optimize its properties? Yeah? And so that's another question that you should then ask and try and figure out. And the other thing is that, well, what you see here, so there's a lot of motion, and this motion is actually thermal fluctuations. So your body is at ambient temperature, so about 300 Kelvin or so, a bit more. And so all the proteins and molecules in your body, I mean, they're in direct, strong contact with the environment, and therefore they suffer thermal fluctuations. And you should also ask yourself, therefore, what is the role of these fluctuations, and how do they cooperate with quantum coherent dynamics, or how are they suppressing quantum coherent dynamics? Yeah, both is possible, and the question is whether there is an interesting interplay, or whether noise just does what we learn in undergraduate physics. It kills all quantum coherence. Right? So that's also a question. And when you understand these things, then you actually can find maybe what we like to call design principles. So I mean, nature had a few billion years to figure out how to do things in an efficient way. So if it can profit from, let's say, quantum coherence or its interplay with environmental noise, there's a reasonable chance that it might have found out how to do that. And there's also a chance that we then sort of can learn one or two tricks from nature to see how to make best use of these properties, either in order to improve, let's say, our small quantum technological devices, or also perhaps if we learn these principles, then maybe we can also improve biological systems, because biological systems, or animals and so on, they are subject to a lot of different evolutionary pressures. So they may not only optimize a small part, for example, the transport process, they also have to make sure that they are optimally protected against environmental influences. I mean, whatever, the sun shining sometimes very intensely and sometimes very weakly, or it has to protect itself against all sorts of enemies and all sorts of things. So natural animals will have to optimize in a very big parameter space. And so sometimes they might not have found the optimal operation, for example, for harvesting light, because they also have to take care of all these other constraints. But we might be able to take animals or plants or so and put them in a very well protected environment where they don't have to care so much anymore about certain other constraints. And then we could make them, or try and make them by whatever genetic engineering, a little bit more optimal, if we know what it means and what we need to do to make them more optimal, right? So that's kind of that's a wild dream. I mean, it's probably 10 or 20 years or even more away. But so in principle, if we learn tricks and we see what makes, for example, energy transport optimal, then we could design also, again, natural beings. And what makes all this for me interesting, and why I sort of started looking into that, is the fact that nowadays there are experimental tools that are sensitive to quantum properties on length and time scales that are really relevant in biological systems. So really very short length scales and very, very short time scales like picoseconds and so on. And so this turns all this from mere theorizing into actually doing theory and making a prediction, and then experimentalists can go and in principle check what you just predicted. And that makes a whole lot of a difference to progress. And also in particular here, because if I make a proposal for an ion trap device, a quantum computer, or some funny little effect that I want to see in an ion trap, if I make the proposal and I write it down, I'm pretty sure that experimentalists will be able to realize it if they have enough money, patience, and so on. Because we know the system very well. So we know the boundary conditions, and I can more or less decide beforehand, this is going to work and this is not going to work. In biological systems, especially in this region, this is much, much less certain. So I can make a proposal or a theory of something, and the problem is that there are a lot of unknowns here. So we do not know these structures to let's say, sub-angstrom precision. And sometimes something like that will be needed to really make an accurate description of the system. So we will make a theory, we will make certain statements. If this and this and this is true, then this should happen. And then you actually have to go to the experiment and you have to look at your real biological system and see whether it really is happening, and it's really not necessarily clear beforehand what you will see. So that's a bit of a difference to kind of quantum technology, where we have achieved such a high degree of precision and control that we know of what will happen. We just have to realize it. Okay. And that's why experimental verification is important. And in fact, so in 2007 there was an experiment that excited quite a few people into looking into these things. That was from the Berkeley group, where they did some laser experiments on photosynthetic complex, and they saw strong indication that there's quantum coherence. And I'll explain you where this is coming from. And so the first time I heard about that was actually in an editorial board meeting in contemporary physics, which shows you that it can be useful to attend board meetings. And so, you heard, I don't know who it was, but someone mentioned, oh, there's this crazy experiment in Nature from some people in Berkeley, and they claim that nature is a quantum computer. And because in the end of this paper there's some sort of statements that are, well, I wouldn't actually subscribe to, where they really think that, well, this might be quantum computation that is going on when you have energy transport in photosynthetic complex. I think this is not such a good statement, but of course, that makes you look into the paper, and so that's what we did. And okay, so now what I want to do is I want to very briefly explain to you what these people saw. Show you a little movie actually with experimental data, so what you see there, and I'll tell you what people infer from that. And then what I want to show you is and really explain to you how it is that actually indeed nature is making use of quantum properties on the one hand, of quantum dynamics, but at the same time of noise. And so it's really an interplay between the two things that optimizes the biological function in this particular case, namely for energy transport. And so now we understand that really fairly well. And it is also, it turns out, that the presence of the environment, so in this case of fluctuations, actually leads to long-lived quantum coherence. So it's actually the presence of the environment that sort of makes quantum coherence longer lived. And so that's also that's certainly, I didn't tell you that in Strathclyde because we didn't have that clear at the time. But it's really a clear example of how environment and quantum dynamics collaborate to live the longest and be the most efficient. And things like those might actually be able also for other things in the future. Right, so quantum biology, well, actually, quantum biology, many people who speak about that, they say, oh, Schrödinger, this and that, in his book about, I think, physics and life and so on, what it's called, I've forgotten.
What is life?
What?
What is life?
What is life, yes. So, and there, well, it's often quoted as sort of the first time that the question was posed how quantum physics actually plays a role in biology or so. It's actually not quite correct because there's a gentleman called Pascal Jordan. He was also one of the pioneers of quantum physics. So there's the famous Born, Heisenberg, Jordan papers, and so he's that Jordan, and he also did a few other pretty good things. And already in the 30s, when you read that book, he was thinking actually about physics and biology, and also quantum physics and biology. And well, he was sharpening his thoughts, and in the end, in 1943, he wrote this book here. And well, so even he gave a chapter, it's called Quantum Biology. And in this chapter here, there's, for example, this sentence in die Gesetze der Atomphysik, Quantenphysik für Lebensvorgänge von wesentlicher Bedeutung. So that means, are the laws of atomic and quantum physics of significant importance for the processes of life? And so he really asks himself whether quantum mechanics, so to what extent it really is relevant for us, biological beings. Of course, at this stage, I mean, it was extremely difficult to make experiments to that extent. I mean, to answer such a question. But I mean, okay, he was thinking about that already. And okay, so much for historical remark and fighting Johan's corner. Right. Okay, so that I actually said already. In quantum technologies, we take ions, we put them in super high vacuum, we cool them to whatever microkelvin temperatures or millikelvin temperatures to bring out quantum behavior. In biological systems, everything is in contact with the room temperature reservoir, and we have to see actually how quantum coherence behaves, how it survives, what relevance it might have, and how it interplays with. Okay, so today I will only talk about this, photosynthesis. I leave out these things, partly because there's much less actually evidence for quantum physics in these two processes, although I believe that quantum physics plays a role here. And so just as a brief introduction, so sometimes people get a bit worried talking about quantum biology because they think they have to know a lot of biology. That's absolutely not true. I don't know very much biology myself. Here is basically all you need to know about photosynthesis for the moment, at least. So that's an example of a particular, or the structure of a particular photosynthetic complex. That's the photosynthetic complex of a small green sulfobacterium. Sulfobacteria do photosynthesis, so they live at the bottom of lakes, the bottom of the Black Sea, and they have also been found actually at the bottom of the Pacific, near black smokers, which is sort of volcanic activity at the bottom of the Pacific, and the rock is very, very hot, and they actually do photosynthesis from the thermal glow of that rock. The rock is 400 degrees hot, and so they are not sitting directly on that rock, but they're a little bit away from it, where they can live. And when you do the numbers, actually, so when you have a 400-degree hot rock, and so you work out how much radiation is emitted at optical frequencies, so where the photosynthetic complex is working, then you see that this is the same amount that these green sulfobacteria will see when they're sitting at the bottom of the Black Sea in about 200-meter deep water, from the light that is coming from the top of the sea down to 200 meters. That's roughly the same amount. That's a bit, one really has to do the numbers. I mean, for me this is impossible to guess, but it's really roughly the same. And at the bottom of the Black Sea, we know that they do photosynthesis. I mean, they get one photon per chromophore, so per molecule that can absorb a photon of light every 8 hours. And so that's really not very much. And as a consequence, they do live a very, very slow life. So they actually multiply roughly every half a year or something like that. When you take them out and you bring them to the surface, they start to live faster. At some point, if there's too much light, of course, they're not used to that, and they will die. But so they are very much adapted to low light conditions. And so you can actually also hope that their photosynthetic complex is optimized to a large extent to really squeeze out the last bit of energy from the sun that is occurring there. So what do you have? So you have 3 parts actually. And so this is what is called the reaction center. So that's a very small, compact part of the photosynthetic complex. And that is the place where in the end the energy that came from the sun is used to first make charge separation and then drive some, in the end, chemical processes. And so there, what will happen is there will actually be some some electron transport taking place and some electron tunneling. And so that's why this part of the photosynthetic complex has to be quite small and compact, because tunneling doesn't take place over huge distances. And also there's basically two solutions that nature has found for the structure of this. So this is quite universal across nature. So this is a small part, and because it's so small, it actually will not absorb very much light itself, because it's just a cross section, so it's very small. And so it turns out that it can process energy 100 times faster than the rate at which it absorbs photons from the environment, roughly. So that means that normally, if it would just be this thing here, it would sit there idle for most of its time. And that's wasteful. And so therefore, what nature has come up with is the thought that, well, okay, we need to have some bigger object, an antenna complex, which is full of light-absorbing molecules, chromophores, which will sit there, and because it's much bigger, it will of course absorb light much more frequently. And it's made such that it will actually, this part will absorb light at about the rate that this reaction center can process energy. Okay. So that's roughly the size ratio, that is much bigger. And then, well, you have this thing, so you have an antenna, so like a TV aerial on your roof, you have the telly in your living room, and so what you need in between is a cable that helps you transport the signal from the aerial to the TV, also from here, from the antenna, down to the reaction center. So there's a connection piece, and this is also a pigment protein complex, so there's this protein that holds together some light-absorbing molecules, but they're quite small. So it only contains 7 or 8 of those molecules. And it's really this part that has been studied in this experiment in 2007 in Berkeley. And it's this part that host dynamics we try to understand. And what we know is that transport through this system, so energy transport, is extremely efficient. It's well above 90%, it might even be 98%. It's not so easy to measure this directly. And so we'd like to figure out why it is so efficient. So what happens? Photon is absorbed here. It turns into, it creates an exciton. This exciton hobbles along here, enters in one place in this complex, transports along. At a different place, it leaves the complex and goes into the reaction center. And so we want to see this process here. Okay. So how do people study that? Well, they take actually, so this is a fast process. It takes about 5 picoseconds or so. So you have to be fast. And well, I mean, you cannot measure these things with electrodes, so you have to use light. And so what you do is, or one way of studying the system, is that you shine in a sequence of fast laser pulses. Each of those is actually only about 20 to 30 femtoseconds long. And so this is made because they want to have this more or less like a delta-like pulse, so an instantaneous kick to the system. And so what they do is, basically they kick the system 3 times, and then they probe the system, so they probe the coherence of the system, basically. Okay? And so then they vary the length, or the time separation between those pulses, and they look at how the sort of the signal comes out, how it emerges in time. So you have 3 times that you can vary. Okay? And so that basically, by kicking a system that you expect to somehow swing, you can, by changing the time separation between those kicks, you can imagine you can learn something about the dynamics of the system. So if you have a swing, you kick it once, or you push it once, right, then it starts to swing. And now it will, the effect of the next kick will very much depend at which time you make it. So if the pendulum has swung back completely and then you kick it again, well, then you put energy into the system and the amplitude grows, for example. If, however, you kick it, it moves, and then let's say you kick it again at the maximum. Well, Right, that's not such a good thing. No, exactly, yeah, that's right. So then it swings back, and you're exactly at the bottom of the swing again, and then you give it another kick, and it will just stop. So, right, so it depends really, I mean, at which times you kick the system. I mean, that will depend on how much energy is afterwards in the system, how much coherence you might have, all these sort of things. So that's sort of I mean, you could even think of classically studying a pendulum by making these kicks and then see how it's swinging afterwards. So it's really, you can view it as such an idea. And so that's what people are doing. And normally, so then they get nice plots like these. So what you normally plot here is you have this time scale, tau, coherence time. And then here you have this little t, this is the rephasing time. And so these are two time scales, and normally it's nicer to plot these things in frequency space, because we're talking about light that we're shining onto the system, and it has a frequency, so it's better to argue with that. And so what you do is normally you measure for different pulse separations here, for different time here, and then you take Fourier transforms, and you have a frequency axis here, frequency axis here, and here you have the response of the system. And then you have things on the diagonal, that's here. And so if you get something on the diagonal, so roughly speaking, what does that mean? Well, that means that you excite the system at a certain frequency, and it re-emits or it reacts at the same frequency. So that could happen if you just have a single site in your system, you kick it, it swings at a definite frequency, and then it re-radiates its energy at exactly the same frequency. So that's kind of a boring process. It just will tell you what are the resonance frequencies of your system. So on the diagonal, you will have a distribution of peaks, and they indicate at which frequencies the system resonates. Then you can have a more interesting process where you start here, you excite the system at one frequency, but then later on it actually re-emits at a different frequency. And so what that means is you have one side, it's getting excited, and then the energy, also in this case the exciton, might move to a different place in the protein, which has a slightly smaller excitation frequency. So for example, it goes downhill in energy, and then it re-emits. And so when you have one of these off-diagonal peaks, that indicates to you that you have had transport in the system, some kind of transport. You don't know whether it was coherent or incoherent, but you know that the energy has wandered from one place to another. And so finally, you want to figure out, is this coherent or not? And so to see that, what you do is you actually make a lot of these plots for different time separations between the pulses 2 and 3. And now there are roughly two possibilities. So one is that really everything is sort of pretty much incoherent. And then what you will see, or what you would expect, is that, well, there's a signal perhaps building, and then it goes to some kind of steady state, or it goes pretty much monotonically to some particular value. That's what you get when you have sort of rate equations in your system, right? So there are no oscillations. On the other hand, if you expect that there's some coherent dynamics, then you expect that actually energy can go back and forth between sites and can oscillate back and forth. And so then you would expect oscillatory behavior, and you would expect actually that, for example, the peak amplitude might oscillate in time. Okay? And by oscillating in time, I mean oscillating in this time difference here. And well, okay, so then they do experiments, and they were looking, okay, what do we see? And they looked, for example, at this off-diagonal peak here, and then they looked at its amplitude, and then you see that there are actually, indeed, oscillations taking place. And that is taken as a good indication, a strong indication that there's coherent dynamics in this system. And really in the transport of electronic excitations. Now this is, at the time they were saying, well, this is really purely electronic coherence. Nowadays we think of this a slightly different way, which I will explain actually. And what was surprising here is the length of these coherent oscillations. So that before they did the experiment, they actually we're expecting that these oscillations would last maybe for 100 femtoseconds, because that's what you're used to in condensed matter physics. So you can make some similar thing. You can create excitons in condensed matter and solid-state physics, and then you look at the coherence time of these excitons, and you will see that they're maybe 100 femtoseconds or so. Here, actually, this is a bit of old data, actually. Lasts even longer, the oscillations nowadays, because the experiments got better. It lasts 10 to 20 times as long. And quite possibly, actually, the coherencies last for the entire duration of the transport process. Right? That's not really proven, because there are some things that cover some of these coherencies, but they live far, far longer than people have expected. And so for a long time, this was actually a mystery. So people made all sorts of theories that try to explain where this is coming from. Because also, again, the feeling was, if we understand that, then we actually learn maybe a nice trick how to prolong the coherence time in natural systems. So now, here's a little movie. So this is, I got this pictures of this movie from Greg Engel in Chicago. Greg was also the postdoc who led the experiment in the Fleming group in Berkeley in 2007. And so he's one of the leaders in these sort of things. And so what you will see here, this is one of these 2D spectra, these colorful dots that I've shown you. And this is the delay time between the second and the third pulse. And so we change this in time now. And what you should see is that actually really this thing is not monotonically approaching a particular steady state value or so, but it's really sort of oscillating. And so we will see that now. We'll see all sorts of things, and it will breathe and grow and so on. Yeah. Right. So, I mean, you see that there's stuff, so this one is going up and down, it's coming again, and it's going down again, and coming back, and so on. And so you see a lot of sort of oscillatory motion in this little movie. At some point you will see a lot of stuff happening up here, and sort of time is growing, and it's certainly not settling down at all, right? So there's really all the time stuff going on. It has a quiet period in the middle, but then it will start again. So up there is now. So it's really, the energy is being shuffled around in the system, and it's going back and forth. It's not just going monotonic, sort of in a monotonic fashion to the whatever lowest energy side. It really moves back and forth. Okay, and so I can let this run for a long time. I think this runs for 1.2 picoseconds or so. But I mean, you've seen the point. So this is real experimental data that people have measured. And so then you can go about this and you say, well, okay, let's do some theory about this. So this is coherent, so let's make the theory for a coherent system and reproduce all the experimental data and prove that it's really a wonderful quantum mechanical coherent system, and all is fine. So that's what we did. So certainly we looked at, so now we simplify really. So this is a little network of sites. Each of them can have one excitation, and these excitations can hop back and forth between those sites and in a coherent fashion. So this is the Hamiltonian, so destroy an excitation in one side, create it in the other side. And so there you have sort of these terms. This is the excitation energy. This is what it costs you to make an excitation in one place. Then you can have energy loss. So these excitons, these are like an optical, and I mean sort of 1.5 electron volt or so excitation. So they have a certain lifetime. They live for about a nanosecond, just like an excited atom lives for for a few nanoseconds perhaps. And so if the exciton sits there for too long, it will just decay and just produce a bit of heat in the environment. So this is not what the biological system wants. And then, so the energy comes in initially in here. So this is the place that is closest to the antenna. And down here, this is the side that is closest to the reaction center. And here is where the exciton is leaving the system and starts to do some sort of chemical reaction. So this is an irreversible process. Yeah? And so it's modeled as such. And then you work out what is the transfer efficiency. So you stick an excitation up in the upper part of the network, And then you ask the question, what's the probability that after a time t it has arrived in the reaction center? And here's picoseconds, time in picoseconds, and you see after 5 picoseconds it's about 50% probability. So we have used parameters that are from the experiment for the Hamiltonian and so on. So we should have put in the right kind of numbers. But I told you at the beginning that the transfer efficiency actually is known to be well above 90%. So there's something missing here, obviously. So it's not correct here. And what is missing is that we ignored the fact that there's actually noise in the environment. And so that means that the protein is actually vibrating because it's at room temperature or at finite temperature. And because it's vibrating, the local environments of each of the sites that we have in this, or these chromophores that we have in the protein, the local environments change a bit. So a hydrogen atom might move a bit farther away or moves a bit closer. So sort of partial charges are moved away from the site or move closer to it, and that changes the excitation energy of each of these individual chromophores. And so that means that the excitation energy jiggles randomly in time. And so that just gives this dephasing that I had also been mentioning yesterday. Right? So you have this dephasing noise. And when you start to put this in, actually you will see that the energy transfer efficiency grows. More noise actually helps you to transport excitations through that system. And when you make a real plot, so then you see when you have little noise, transport is bad. Then you have more noise, it gets better and better up until it reaches some sort of plateau. And then when you have too much noise, then the transfer efficiency actually goes down again because you enter sort of a quantum zero regime. When you just have too much noise, then there's just no evolution whatsoever. Okay? And so everything stops again. And so then you can ask yourself, well, this is sort of an intermediate regime. So there's a bit of noise here, it's not too much, not too little. So, but what does it mean? How much noise is there now? Is this so much noise that everything is well described by a bunch of rate equations? Or is it so little noise that actually everything is pretty well described by a bunch of sort of Bloch equations like you use in or master equations like you use in quantum optics, where you have a bit of noise perhaps that you use in a perturbative fashion? And the answer is that it's neither. It's actually sitting right in the middle in a very awkward regime, where the interactions within the system, so the interactions between these different chromophores, are roughly of the same strength as the interaction between the system and the environment. And so the environment is neither very, very strong, nor is it so weak that it can be treated perturbatively. So that's already sort of an interesting thing. And now I'll give you one reason why this should be like that. Because now the question, of course, is this an accident? Could it not be that maybe nature was just not clever enough and didn't protect itself well enough from the noise, and it would really, maybe in 300 million years, it will have evolved into a state where there's almost no noise anymore, for example. So, and I'm telling you now that no, it will not do that, because this is the optimal way. And so to see this, I'll pose a little problem. So we did this actually and also really like that. So now again, so this is one side, it has a certain energy for excitation, and so this is where the excitation will come in. This is the side in energy which is closest to the reaction center. It has a lower energy actually. This is also like that in reality. So things tend to go down in energy fun. And now the interaction between different sides is dipole-dipole interaction. And so what I'll allow you now to do is the following. So you have this side is fixed energy, that side is fixed in energy. Now I allow you to give a third one. And this side, you can choose the excitation energy, and you can choose the interaction strength with this side here. And now I ask the question, what is the optimal choice? And optimal, optimal is defined as what choice will make the probability that the excitation reaches this place after 5 picoseconds the largest. Okay? So that's a question. And now you have two choice. Well, I mean, as such, you cannot actually answer this question uniquely. So first, what you have to specify is you have to learn something about the way the environment is fluctuating. And we had this yesterday as well. What you have also in these proteins is that very low frequencies, there are not so many fluctuations. Very, very high frequencies, there are also not very many fluctuations, so not very many vibrational modes. And somewhere in the middle, there's a maximum. Okay. So that's roughly how the spectral density looks like. It is low for low frequencies, and it rises over a maximum, then goes down again. In reality, it looks a bit more complicated, but that's the general principle. And now you have two possibilities. Either you think, or you switch on a computer. And so we did both. So we switched on a computer and sort of ran an optimization algorithm, and this is not a very difficult optimization problem. So you will find actually the optimal solution for placing this site and choosing its interaction strength. And the answer is that you find this. So the best choice is, that's what the computer says, that this extra level here is close in energy to the first one, and it's interacting quite strongly. I mean, it has a quite strong coherent interaction. Okay, so that comes out of the numerics. Now, why is that? Now, you could have guessed this from the beginning by thinking first. And actually, it is very similar to what I told you yesterday about the diamond sensor, how it actually senses other spins in the environment. So now here we are sensing fluctuations in the environment. So what you have here is, you have here two levels. They're strongly interacting coherently. So best thing is you go to the dress state basis. So you have coherent superposition, 1 plus 2 is up here and 1 minus 2 is down here. And they have a level splitting, these dress states, that's proportional to the interaction strength here. Okay? Now, furthermore, what was dephasing in the original basis now makes amplitude, so makes jumps between the energy levels of, in the dress state basis. So dephasing here, sigma z, and it turns in the dress state basis into a sigma x, interacting with the environment. And so this is exactly what you want. You want to jump between energy levels to have transport. So what the system is doing here, it is basically using the coherence in the interaction to split up the energy levels. So it's in such a fashion that the energy difference matches the maximum of the environmental spectral intensity. So it probes, or it tries to be sensitive to that part of the environment that is fluctuating the strongest. Yeah. So that's the explanation why the computer found that solution. But of course, you could have guessed already that this might be the solution. So now you could say, well, okay, this is mathematics. Is that really what nature does? And the interesting thing is that when you look at this FMO complex on which all these experiments were done, you find exactly such a structure. So you will find two levels that are close together and interact quite strongly, and then the third one is closest to the reaction center that actually, well, that's sitting down here. And the spacing, I mean, so here you have this interaction strength and so on, and the spacing of these stress states indeed matches what is expected or to be roughly the maximum of the spectral density of the environment. So it may be actually that nature has optimized itself in that respect. And now you also see why an intermediate amount of noise and coherence should be the optimum thing. Because if there was no noise, well, then you wouldn't have any transitions between those stress states, so there would be no point in doing this in the first place. You would not benefit at all. On the other hand, if the noise is extremely strong, it's so strong that actually the dynamics is not coherent at all, you will not actually get this level splitting there at all. So somewhere in the middle, when the noise is not too strong and not too weak, should be the optimum. And so this is just one example. There are 2 or 3 other processes that give the same conclusion. It's always such that for transport, an intermediate amount of noise tends to be the best. Right? So that shows you already that the protein environment, the vibrations and so on, is really useful, or might be really useful, and nature has probably made use of it and has optimized the rest of its structure towards that. Now, there's still this thing in 2007 that did the experiment and they said, oh, these coherencies live really a lot longer than we thought. And there was no explanation for a long while. Now, it turns out that almost certainly the explanation for that is also because there's this protein environment that is vibrating. And actually, I will explain you now in a very simple picture how this protein environment might actually create coherencies in the system. So, and really, I mean, no equations, just a few pictures, but that explain just the principle of it. Now, this is your whole system in the ground state, so no exciton, no excitation in the system. And this here is a pendulum that indicates a particular vibrational mode in the environment. So these proteins actually have, on the one hand, sort of a very broad spectrum of, not very well-defined modes. I mean, it's just a continuum. But they also have actually vibrations that live for quite a while, so at least a few picoseconds or so. Now, they are showing up in the environmental spectral density as quite narrow peaks, and they can be seen in experiments. So this is one of those modes, is this pendulum here. Okay, so that's sitting in the environment, and so initially everything is in equilibrium, more or less. So there are small fluctuations of this pendulum, but all the protein is near its ground state, so the nuclei are just juggling around this equilibrium position. Okay, now we excite the system, so we put an excitation into the system. Okay, so now there's an exciton and it's sitting in one of these excited states. So you have many energy levels here. You have 7 sites all interacting, so you have 7 eigenstates for a single exciton rotation. And you're seeing that the spring that couples the exciton to this environment has been compressed a little bit. The environment is not in equilibrium anymore. What has happened is now you have sort of an exciton there. Well, this is like a little dipole. It sort of tears at its environment and it changes the forces a little bit. So what was before the equilibrium position is not now the equilibrium position anymore. And in particular, for this vibrational mode, well, what it will do now is the spring has been compressed, so this pendulum will start to swing. So in other words, this protein will start to make coherent oscillations. Yeah, so it's swinging back and forth, so it starts basically here, and so it swings back and forth. Well, if it does so, well, then at some point this spring will actually be stretched, and so we pull the exciton. And so we might actually transfer energy from this vibration onto the exciton and move it from one side to another. And so it might actually not only move down in energy towards a low energy state, but it might actually also be pushed up again. And because this little pendulum here is swinging periodically, so coherently, this force is actually also a coherent force, and it makes coherent oscillations of this exciton between different sites in this system. Okay? So that's really the idea, and you can view this almost, you can make a very simple theoretical model which sort of gets it roughly right, not exactly, where you think of this as basically a periodic driving force. So you start with a pendulum in a coherent state, and in quantum optics you would say, well, okay, this was the vacuum, now it's in a coherent state, so we make a Glauber transformation, and we transform the environment into the vacuum state again, and what happens is that in our Hamiltonian there will be a classical field appearing, a classical driving field. That is normally the Hamiltonian that you write down when you do quantum optics. You write a classical laser term into the Hamiltonian. So it's the same thing here. So in the end, if you do a transformation, you see that there's just like a coherent driving force here on the electronic degrees of freedom. And so it's really this environment, this protein vibration, that coherently jiggles around the exciton, and this is what you see as coherent, long-lived oscillations in these 2D spectra. Okay. And so, in a way, it's environment-assisted coherence that you have. And so, in the picture before, so you have here this energy separation, and now you don't only have this background here, but you actually also have a very sharp peak on the spectral density. And if this sharp peak, so the frequency of this pendulum, is well matched to this energy difference, then it will have a big effect. Well, and this is how the spectral density actually looks like. So you see here a peak, here a peak, here a peak. So there are several peaks. So you can actually really see them. You can measure them. And they're not terribly narrow, of course, because these measurements are not very precise. But they definitely are there. And now you can do a lot of numerical calculations and so on, and put on all a million details. And you can see that this is a reasonable explanation. But this is the basic principle by which the environment actually creates coherencies in the photosynthetic complex. Well, that's the experimental proof. I mean, I put it in because the last time I spoke about that, people were laughing when I forgot to actually put that in. So you see, actually, so here, you cannot see the left-hand side. So here are sort of coherencies between excitons, and so the dashed line is when you don't have any sharp mode in the environment, and then you see there's a bit of oscillation, but it dies out very swiftly. And here the blue one is when you have a well-defined mode in the environment, one of these pendular basically, and then the system oscillates for a much longer time in fact. Okay, and so you can really see that this is happening. And I think I ignore this part because it's not really, it's just maths. So really, I think what is becoming increasingly clear in this quantum biology stuff is that it's really, what is really important is not only there might be some coherence or so, what is actually really important is that you have on the one hand coherent dynamics, on the other hand you have your protein environment that holds everything together. That is vibrating, has thermal fluctuations, has mode structure, really is a non-trivial environment. And these two things, they are collaborating, and it's only when they're well matched that everything works optimally. And that's where nature might have really made an effort to bring things together. So the vibration spectra, for example, may well be, it seems to be quite universal, so there's always this maximum at around 1/60th of an electron volt or so. And this is more or less seems to be a given. And what nature could do, for example, is, or was able to do, is it could arrange its chromophores in a particular way. The closer they are, the stronger they interact. The farther they are, the less they interact, for example. It can adjust the local environments of these chromophores by putting a few partial charges a bit closer and therefore increasing the excitation energy or decreasing it. So it can fashion its electronic network, basically, by placing chromophores in the right places and adjust them to the presence of this environment. And it turns out that the best is really to keep a little bit of quantum coherence, but not, not to keep the system completely 100% coherent. And well, when you study this in much more detail, and you find a few more processes and examples and so on, where you can see how to make a network optimal. And in this case, for transport, when you are bound to be in some sort of slightly noisy environment. Okay. And that's, of course, that's sort of kind of good to know, because transport of energy is an important part of photosynthesis. But actually, a reason why this is also interesting is because everything I've told you here, I mean, sometimes I said excitons, sometimes I just said excitation. It really didn't matter so much that I was talking about excitons. Same principles are also relevant for electron transport. And electron transport is also a very, very important part of biology, not only in photosynthesis, but generally in the function of proteins here. And in the reaction center, there are indications that all these little things that I've shown you here actually play a role and assist this fact that excitons are
manipulated and ripped apart, and there's charge separation. This is aided by vibrations in the environment, almost certainly. And understanding this will be really important for us to really understand what is happening there. What it might also help us to understand how, for example, proteins react when there's a pharmaceutical molecule coming and docking to a receptor. There are things happening there. There might be electron transport happening. To understand this, you will have to understand the vibrational environment as well and put these things together. And so this is much more far-reaching than, well, potentially, than just looking at photosynthesis. And generally, I think it's nice. I mean, I always liked this idea from a zillion years ago already that environments might actually, environmental noise might actually be helpful for you to create coherence and facilitate coherent dynamics. And so that's an example where it might really play a significant role. And my time is up. Thank you.
We have time for a couple of questions, if there's anybody.
Could you kind of envision being able to learn from these biological systems in terms of quantum information processing?
Well, I think at the moment I would say rather not, because the goals are quite different. Yeah. So this, I mean, nature is not so much interested in making coherent quantum computations or so. It really is interested in making some interactions, transport stuff around. So I think the goal is slightly different. It's not impossible, of course. I mean, in principle, you can even drive a quantum computation by noise. But I don't think that this is what nature has been doing and has been aspiring to. At least that's the way it looks at the moment. So I would say probably.
So in those experiments that you put up, they were done at different temperatures. And it seemed the coherence was there at 77 Kelvin or whatever it was, and then it sort of disappeared as you went up to room temperature when the systems actually operate. So it was the
That's partly this is because this is not the freshest data on the planet anymore. So there are certain things that actually makes you think that coherence lives less long than it actually does, because these are ensemble experiments. Okay. So in fact, what you have is you have 10 to the 12 roughly of these of these photosynthetic complexes. They are not identical, of course. So they have quite a bit of broadening. And so just inhomogeneous broadening, for example. And that will cloud some of the coherence that you can observe in the experiment.
And some of these spin echo pulses to correct for that experiment.
Well, actually, in a way, this experiment, I mean, this four-wave mixing spectroscopy is a little bit of that in that direction, but it's simply difficult to read because the broadening is quite strong. So it's difficult to extract the single complex behavior from that. However, there are a variety of groups that do single molecule spectroscopy, not exactly on this one, but on others, with slightly different methods, and they see long-lived coherence. And also, now the experiments here are improving. So the last things that Greg told me was that you had 2 picoseconds worth of oscillations. At 77, for example, when I showed you this probably was maybe half that. Yeah. So they improve the experiments, they see longer and longer coherence. So it's likely actually, it's quite possible, certainly our calculations suggest that it might extend for the entire transport process, which is only about 5 picoseconds, and most of it is actually finished after 2. So there is, but I mean, you are right, one had to be very skeptical about this at the beginning, whether this is really a low temperature phenomenon, but it doesn't seem to be. Yeah.
Is it anything like the classical phenomenon, stochastic resonance, where you sort of have environmental noise and then it makes it easier to pick a system between different steady states.
Well, actually, 12 years ago or so, we wrote papers on stochastic resonance and quantum mechanics with a dream of using sort of these resonances to drive a quantum computer. It is similar, let's say, but it's not the same, right? It's also a noise-assisted phenomenon here, but it's not quite the same because we don't have this sort of, I mean, well, we did not manage to interpret it in this way, let's say. Maybe if you find a clear interpretation in that form, it's fine, but there's no strong nonlinearity in the system. But you have this picture of double well potential that is sort of moving back and forth, and then you need a nonlinear response in the system to the noise so that you get, in the end, a coherent response in the system. That's not quite like this. But it falls into the same ballpark of phenomena where you have a collaboration between coherence, driving, weak driving, and noise to get some enhancement of the response. And I believe that there are other instances in biological systems where stochastic resonance, I mean, even at the level of really very, very small systems, will play a role. Also.
Right, that's all. Thank once again.